Article 430, which addresses motors, motor circuits, and controllers, contains information relevant to manual motor starter horsepower ratings. Specifically, Section 430.31, concerning motor branch circuit short circuit and ground fault protection, provides guidance. Subsection B, motor overcurrent protection, Item 7, manual motor controllers, states that a manual motor controller shall be permitted to have a horsepower rating not more than the motor it controls. There are exceptions to the general rules for motor branch circuit short circuit and ground fault protection. Exception number 4 states the continuous current rating of the branch circuit short circuit and ground fault protective device shall be permitted to exceed the motor full load current, single phase, by more than 6 times but not more than 10 times for motors with a marked code letter F only. Exception number 5 states that the continuous current rating of the branch circuit short circuit and ground fault protective device shall be permitted to exceed the marked full load current of a single motor branch circuit supplying a motor or motors with a marked code letter G only, by not more than 8 times. Article 100 provides relevant definitions. The horsepower rating definition states that it is the nominal full load power output of a motor in horsepower. Based on these code provisions, a single-phase manual starter can start motors up to 1 horsepower with a marked code letter F. A 3-phase manual starter can start motors up to 10 horsepower with a marked code letter G. It is important to note that the horsepower rating of a manual starter may be different from the horsepower rating of the motor it controls. The starter's horsepower rating must be equal to or greater than the motor's horsepower rating. To elaborate further, consider the implications of Article 430. Firstly, the selection of a manual motor starter involves ensuring that the starter's horsepower rating matches or exceeds the motor's horsepower. This is crucial for the starter to handle the motor's full load current and starting current without being overloaded. Secondly, the exceptions related to motor code letters F and G highlight the importance of understanding a motor's specific characteristics. These code letters relate to the motor's inrush current during startup. Motors with code letter F have a different inrush current profile than motors with code letter G, and the code allows for different levels of overcurrent protection accordingly. Thirdly, the branch circuit short circuit and ground fault protective device, such as a circuit breaker or fuse, plays a vital role in protecting the motor circuit from faults. The allowable increase in the continuous current rating for motors with code letters F and G acknowledges that these motors may draw significantly high current during startup, and the protective device needs to tolerate this inrush current without tripping unnecessarily. Furthermore, the manual starter's function is to provide a means of manually starting and stopping the motor. It typically includes overload protection to protect the motor from damage due to sustained overcurrent conditions. This overload protection is separate from the branch circuit short circuit and ground fault protection. The overload protection is designed to trip at a lower current level than the short circuit protection, providing a more sensitive response to overloads. When selecting a manual motor starter, it is essential to consider the motor's voltage, full load current, horsepower, and code letter. The starter's voltage rating must match the motor's voltage. The starter's horsepower rating must be equal to or greater than the motor's horsepower. The starter's overload protection must be properly sized to protect the motor from overload. The branch circuit short circuit and ground fault protection must be selected in accordance with the NEC requirements, taking into account the motor's code letter. In addition to the NEC requirements, manufacturer's specifications for manual motor starters should also be consulted. These specifications provide detailed information on the starter's capabilities and limitations. For example, the specifications may indicate the starter's maximum voltage rating, maximum horsepower rating, and overload protection range. The specifications may also provide information on the starter's short circuit current rating, which is the maximum fault current that the starter can safely withstand. When installing a manual motor starter, it is important to follow the manufacturer's instructions and all applicable electrical codes. The starter should be mounted in a suitable enclosure to protect it from environmental conditions and physical damage. The wiring connections should be made securely and in accordance with the wiring diagram. The overload protection should be properly adjusted to protect the motor from overloads. After installation, the starter should be tested to ensure that it is functioning properly. The motor should be started and stopped several times to verify that the starter is operating correctly. The overload protection should be tested by simulating an overload condition. If the overload protection trips, it should be reset and the cause of the overload should be investigated. Regular maintenance should be performed on manual motor starters to ensure that they continue to operate safely and reliably. This maintenance may include inspecting the starter for damage, cleaning the contacts, and tightening the wiring connections. The overload protection should be periodically tested to verify that it is still functioning properly. Furthermore, it is important to understand the difference between manual motor starters and other types of motor controllers, such as magnetic motor starters and variable frequency drives. Manual motor starters are the simplest type of motor controller, providing basic on/off control and overload protection. Magnetic motor starters use electromagnetic relays to control the motor, providing more sophisticated control options such as remote control and automatic starting and stopping. Variable frequency drives provide the most advanced level of motor control, allowing for precise adjustment of the motor's speed and torque. The choice of motor controller depends on the specific application requirements. For simple applications where basic on/off control and overload protection are sufficient, a manual motor starter may be the most cost-effective option. For more complex applications, a magnetic motor starter or variable frequency drive may be necessary. The NEC provides detailed requirements for the installation and operation of all types of motor controllers. These requirements are intended to ensure that motor controllers are installed and operated safely and reliably. In addition to the NEC requirements, manufacturers' specifications for motor controllers should also be consulted. These specifications provide detailed information on the controller's capabilities and limitations. In summary, selecting and installing a manual motor starter requires careful consideration of the motor's characteristics, the application requirements, and the applicable electrical codes. By following the guidelines outlined in the NEC and consulting manufacturer specifications, it is possible to ensure that the motor starter is properly sized, installed, and operated safely and reliably. Remember to always consult with a qualified electrician for any electrical work. The information provided here is for educational purposes only and should not be considered a substitute for professional advice. Proper understanding of electrical code and safety practices is essential when working with electrical equipment. A correct installation or maintenance can lead to serious injury or property damage. Always prioritize safety and seek professional assistance when needed. Furthermore, when dealing with motor control circuits, it's important to understand the concept of control voltage. Many motor starters, including magnetic starters, use a separate control voltage to operate the control circuit. This control voltage is typically lower than the motor's operating voltage, such as 120 volts or 24 volts. Using a lower control voltage improves safety and simplifies the control wiring. The control circuit typically includes push buttons, selector switches, and other control devices that are used to start, stop, and control the motor. The control circuit also includes safety devices, such as overload relays and limit switches, which are used to protect the motor and equipment from damage. When troubleshooting motor control circuits, it's important to check the control voltage first. If the control voltage is not present, the motor starter will not operate. The control voltage can be checked using a voltmeter. If the control voltage is present, the next step is to check the control circuit wiring for any loose connections or broken wires. The control circuit wiring can be checked using a continuity tester. If the control circuit wiring is intact, the next step is to check the control devices such as push buttons and selector switches for proper operation. The control devices can be checked using a multimeter. If the control devices are operating properly, the next step is to check the motor starter components, such as the contactor and overload relay for proper operation. The motor starter components can be checked using a multimeter. In addition to troubleshooting, it's also important to perform regular maintenance on motor control circuits. This maintenance should include inspecting the wiring for any damage, tightening any loose connections, and cleaning any dirty contacts. The motor starter components should also be periodically inspected and tested to ensure that they are operating properly. By performing regular maintenance, it's possible to prevent motor control circuit problems and extend the life of the equipment. Remember that working with electrical equipment can be dangerous, so it's important to follow all safety precautions. Always disconnect the power before working on any electrical equipment. Use insulated tools and wear appropriate personal protective equipment. If you're not comfortable working with electrical equipment, it's best to call a qualified electrician. In addition to the above considerations, it is also beneficial to understand the different types of overload protection available for manual motor starters. Overload protection is designed to protect the motor from damage due to sustained overcurrent conditions. There are two main types of overload protection: thermal overload relays and magnetic overload relays. Thermal overload relays use a bimetallic strip or a melting alloy to sense the motor current. When the motor current exceeds the relay set point, the bimetallic strip bends or the melting alloy melts, causing the relay to trip and disconnect the motor from the power supply. Magnetic overload relays use an electromagnet to sense the motor current. When the motor current exceeds the relay set point, the electromagnet pulls in an armature, causing the relay to trip and disconnect the motor from the power supply. Thermal overload relays are the most common type of overload protection for manual motor starters. They are relatively inexpensive and provide reliable protection against overloads. Magnetic overload relays are more expensive than thermal overload relays, but they offer faster response times and more accurate overload protection. The choice of overload relay depends on the specific application requirements. For most applications, thermal overload relays are sufficient. However, for applications where fast response times and accurate overload protection are required, magnetic overload relays may be necessary. When selecting an overload relay, it is important to choose a relay that is properly sized for the motor. The overload relay's current rating should be slightly higher than the motor's full load current. This will allow the motor to operate normally without tripping the overload relay. The overload relay should also be selected based on the motor's service factor. The service factor is a measure of the motor's ability to withstand overloads. Motors with a higher service factor can withstand higher overloads without being damaged. The overload relay's service factor should be equal to or greater than the motor's service factor. In addition to selecting the proper overload relay, it is also important to properly adjust the overload relay's trip current. The trip current is the current at which the overload relay will trip and disconnect the motor from the power supply. The trip current should be set as low as possible without causing nuisance tripping. Nuisance tripping occurs when the overload relay trips unnecessarily, interrupting the motor's operation. To avoid nuisance tripping, the trip current should be set slightly higher than the motor's full load current. After the overload relay has been selected and adjusted, it is important to test the overload relay to ensure that it is functioning properly. The overload relay can be tested by simulating an overload condition. This can be done by increasing the motor's load or by applying a voltage to the overload relay's test terminals. If the overload relay trips when an overload condition is simulated, it is functioning properly. If the overload relay does not trip, it may be defective and should be replaced. Proper selection, adjustment, and testing of overload relays are essential for protecting motors from damage due to sustained overcurrent conditions. By following these guidelines, it is possible to ensure that motors are properly protected and that their lifespan is extended.